I'm very certain that most of us have talked about free body diagrams first, or at least took classes where you needed to define free body diagrams and also complete them. However, I learned through many years in the classroom that some students have a different understanding of free body diagrams than others. So therefore, it is my goal to define them here on this page and to explain to you what we really need in engineering mechanics. Every time you're looking for full points on a problem where a free body diagram is requested of you, you need to have all the proper tools and the proper definitions in place. So let's get started and talk about that. So number one, the free body diagram is really a representation of a physical system, right? So it's a representation of a physical system. So therefore, you have to reflect reality. And that means you cannot leave anything out, right? So you cannot ignore important components. So let's say, for example, you forget a cable. In real life, the structure would fall down. So that is not acceptable in a free body diagram. And what that really means for us in the class is that we have to include all forces acting on the system. So must include all forces acting on the system. And all is a very important term here. So that means that you have to include all known forces but also all unknown forces. That means you have to develop a solid understanding of what is going on in the system. You cannot just add what's there, which would be the known forces. Much more important, you need the unknown forces. And of course, I will describe this to you when we go through an actual example. You also need to include all force components. So that effectively means that you have to include the X components, the Y components, and if we talk about 3D, the Z components. So in other words, we're talking about the 2D description here and the 3D description here. That is, of course, not a secret to you. But these components take us to the next important aspect of these free body diagrams, which is proper naming. So all of these components and everything you put in a free body diagram has to be properly named. So each component must be named. In other words, you talk about your X, Y, Z components. So let's say you have F1X, you have F1Y, that needs to be clear where that is, and maybe even F1Z, etc., etc. So that's the naming. Besides the name, you also need to include the direction. So clearly show direction. What do I mean by that? I mean that it's not enough to simply draw a coordinate system, let's say. Let me draw one here. So you have a coordinate system, and then it's not enough to just put a force in here. Let's say this is my F1. And then to show the components, you would, let's say, use these dashed lines. And that is often where students stop, but that is not enough. You have to clearly show in which direction they move. So for example, you have to understand that this is going in this direction and this is going in this direction. And so to properly name this here, this would be F1Y and this would be F1X. So that has to be clearly shown. So in other words, when we talk about clearly show directions, you have to provide arrowheads in any direction, not just if it coincides with the XYZ direction. It does not matter. You always have to show the arrowhead, even if it's like a diagonal line or whatever you have in your diagram. Always include that. And then, of course, you have to include the angles. Let's add that. So include angles. And in this picture here, it would be, of course, this alpha angle that needs to be included as well. You, of course, also need a coordinate system. So must include coordinate system. So you need to provide a proper reference. So for example, here is X and Y. And then a few other things that can or cannot be part of your free body diagram, or that may or may not be part of your free body diagram. So for example, sometimes you have masses in there. So masses are represented by particles. Which of course is an idealization, so this is not true in real life, but it is representative of the mass and not the volume. We talked about this at the beginning. So ignore volume, only worry about the mass. And then you find that you have cables, of course, and those are represented by straight lines. Which is again an idealization. This is not true. So in reality, a cable always has self-weight, and therefore it's usually hanging a little bit through. In fact, that has something to do with Newton's third law, that you understand that the cable cannot be straight, because if the cable has weight, then it has to hang down. But that is something we don't worry about in this case. But let me very clearly state that cables can only be in tension and never in compression. And half of you are sitting there probably right now laughing about this statement because they think it's very clear, but you wouldn't believe how often this goes wrong. In fact, let me highlight this. So only tension is very important, because sometimes you may understand this physically and you would never answer this incorrect in your real world examples, but when you run numbers, you sometimes forget it, or students sometimes forget this. And I had a teaching assistant once who said that the students always come up with a compression cable. They came up with like a new invention called the compression cable. But I encourage you to take any cable, take your USB cable that's probably laying right next to you right now, and pull on it, and you will see that it will resist. But as soon as you push on it, it will not provide any resistance. And that should be clear. And when we talk about the next example, or the upcoming example, I will come back to that statement, because it's so important for the interpretation of the free body diagram and all the drawings that you will complete. You also find sometimes springs in your free body diagrams, so springs, which we have a whole lecture dedicated to upcoming, but just so that you're aware here, since we're talking about free body diagrams, a spring would look something like this. This is not a resistor, so this would be a spring, and a spring usually has a spring constant. Called K. And we will have a whole lecture devoted to how to interpret this and how to deal with the spring constant and such. You will also sometimes find that there are pulley systems. And for those pulley systems, please understand that they only redirect the force. Only redirect the force. So they don't add or subtract any force. So let's say you have a pulley here that is hanging on the ceiling, and you have a force in a cable that's going in this direction, and let's say you have a box hanging here. Then the box, of course, is attracted by gravity and it wants to pull down, and there's tension in this part of the cable here, and that is no different from the tension here. So those pulleys only redirect the force, they don't change the force. That is very important to understand for some problems that you solve. Now let's, just for completeness reason, draw a proper free body diagram of all these conditions. I'm going to leave the springs and the pulleys out, but let's just draw a force system that is, let's say, a force going in this direction and a force going in that direction. And then we have a force pulling down. And now I'm going to call this here F1. And then there's a force F2 and F3. And this is sometimes the free body diagram that students present to me when I ask them to draw a free body diagram in an exam. And of course, that is not enough to get, let's say, 10 points. So the first thing you need is a component for each of these forces. So let's do that. And remember that when we draw components, we always have to include the direction. So let's say this and this and this. And we need to include names: F2y, F2x, F3x, and F3y. And that is still not done, because remember, we need to include angles. So let's call this alpha and this beta. Of course, you use numerical values there sometimes. But now we're still not done. We need a coordinate system, and it does not matter where you put the coordinate system. So I'm going to draw two for you here. Some students prefer to put it here and then have the y-axis here. That is acceptable for sure, and what often students prefer. However, an alternative would also be to put the coordinate system somewhere here in the upper right corner, and that needs to be included. So x, y, either one of these will work. Now let me explain to you real quick how I now, with this completed coordinate system, design my point system on exams, for example. So let's say you are asked to draw a free body diagram for 10 points. I will then look at it as complete, and I will deduct points for everything you miss. So let's say you forget to name this F2, you lose 1 point. Let's say you forget to add the arrowhead here, you lose 1 point. Let's say you forget this vertical line, you lose 1 point. This is 1 point, 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 and so on and so forth. Don't worry, when you count this through, you will find that you can actually end up with negative points if you start with a 10-point problem, but that I do not do. So, but it's very common that when students only draw this line here, or these lines that they are used to from previous classes, that then they get like 0 points or maybe 2 points just for effort. That was pretty much non-existent. But understand that each of these makes a point in the exams. Please keep that in mind, because it's points that are so easy to make and where you do not have to lose anything. All right, before we move on to actually apply all these rules and to make use of our free body diagrams and equilibrium conditions and equations, let's talk about one important thing that relate to these free body diagrams. And that is that it is actually an idealization. It represents the physical world, but it is not the physical world. So what do I mean by this? Often I see students actually dealing with this from a real life perspective. So let's redraw the system as it would look in real life. This here with my three forces. Let's say I have a force here, and then my F2 is acting in this direction, and my F1 is going downwards. And let's say it is a traffic light that is hanging on the wall. So that would look like this. And for better interpretation, let's now give them names. So let me call this here node A, this is node B, and this is node C. And now the students have to draw the free body diagram, and I'm nice enough to always say for node A. So I ask them to draw the free body diagram for node A. And if they were to draw this, which they sometimes do, in fact, let me show you how they sometimes do it. They just go in and draw it like this. And they have not understood that this is not a free body diagram. A free body diagram is what you see here, which is actually node A released. So let's talk about that on conceptual level so that you understand that this here this I call a cut cloud, and really what this is node A, right? So it's node A, the one that I have right here. And I released node A from the entire system, and I did not include whatever is going on here and here and here. So that is important to understand for a reason that I will explain to you further in just a second. But for now, let's continue to understand that this is a released node and this has no dimensions, right? So this part here can be 5 meters long, it can be 10 meters long. It doesn't really matter for this picture to be true. So what I mean by that is my cut could actually be represented by something as little as here. So I could release it there, or I could even release it here. And that does not make a difference to my cut cloud that is given to you here. And now if we understand that, we are actually ready to understand the concept that is on the heart of this lecture and that engineers use to really always determine unknown forces. So how do engineers really get to the point of calculating the tensile forces in such cable structures, let's say for a traffic light? So they draw this free body diagram, and what they really do is they include the known force. Let's say the traffic light has a known weight, F1, and then they don't know what F2 and F3 is, but they know that you have to pull back, you have to pull upwards to get that done. So let me develop this for you one last time. So I'm going to draw the free body diagram one more time, but now with the concept of let's find the unknown forces. So I initially have a cable that hangs in this direction. I have a cable that hangs in this direction, and I have a cable that is acting downwards. And now I know as an engineer what the force usually is, because this here has a mass, right? And you can multiply that by gravity to find the force. So this can turn into a force. And I can know that force. And because it's acting vertically downwards, because it's going in this direction, I know what that is. And let's pretend for a second that it's just 1 Newton, right? So let's say it's 1 Newton. Whatever it is, doesn't really matter. And the question is, hey, how do I find the force in this cable and the force in this cable? And I, as an engineer, just provided the cut. right? So I cut this off. That is where I released my node A. And what would happen in real life, you can really visualize this by thinking of these two strings or two cables, and there's 1 Newton hanging on it, and then you take a pair of scissors and you cut them. What happens? The whole thing falls down because there's 1 Newton acting on it. But for it to not fall down in real life, the engineer has to provide as much force in this cable and as much force in that cable as it was originally provided before it was cut. And by that I mean this state here. So here you see the entire body where the support here and the support here really keeps the tension in the cable. And if I cut it here, let's say, and I cut it here again, the system would fall down, and therefore it would not be in balance. So the engineer brings it back into balance by actually adding that force. And it's an unknown force, right? So here we call this F3 and this F2. And F2 and F3 is really the force that is actually acting in this cable. And the trick that we use is the free body diagram, and then later on the equilibrium equations, to really calculate how much force must be in this cable and in this cable for this node not to fall down, right? Remember, this is node A. And the reason I'm repeating myself here over and over again and explain this one more time in a free body diagram, the real world, and then developing the free body diagram, is because this concept here, where I cut it first and then I bring in the forces, is so important, because that is the trick that engineers always use. So engineers really always check, like, what happens if I remove the force that holds it in place. So before I drew this F2 on here, I had nothing acting here that moves in this direction, and therefore it actually would fall down. The whole system would fall down. And so my trick was, I removed the force really, and then I brought it back in. And this is the real concept that we're going to do so many times when we start actually calculating support reaction, like how much force is acting here on the wall, and so on and so forth. We will first remove the forces that we don't know, and then we will calculate or analyze how much it takes to bring it back into equilibrium. And that is an important concept. And the last thing we really need to understand what free body diagrams do for us and how they relate to the equilibrium conditions and equilibrium equations. So to close that circle, here you see this picture on the previous page where we have everything in the x direction that needs to be in equilibrium and everything in the y direction that needs to be in equilibrium. And we can use this free body diagram now to complete our equations and to then analyze the systems using the equilibrium conditions. So let's move on to examples.